welcome to another video. In today's video, we're going to be going over one of those calculus topics that's attached to physics. So, as we all know, Newton was a great mathematician, but even more so, he was a physicist. So calculus does come up quite often in physics. In fact, you cannot describe the natural world without calculus. And even if you're taking a physics class like general physics that uses algebra, all the formulas you will use are derived using calculus, or at least I would assume the majority of them. So we're really just going to be talking about a very small portion of calculus today, and that is work. Okay, so work is defined as force times by distance. So really, this might come out to be an algebra problem starting out, but we're going to move on to how to use this with calculus here in a moment. So we might want to ask how much work is done when lifting a 200 kilogram, I suppose, object, I didn't state what it was, from 1.5 meters to 2 meters. Well, so for this first one, what we're going to do is we're going to find the change in x, or the distance between these 2 points. Okay, and to find this, we just have to take 2.0 meters minus 1.5 meters, and we get an answer of 0.5 meters. However, how do we find the work? And you're going to have to go back to physics for this, but I'm going to say acceleration is approximately equal to 10 meters per second on Earth. Meters per second squared. Now, it's important to note that it is actually 9.8 meters per second squared, but for purposes simplifying calculations like you'll do in something like AP Physics, I'm just going to say 10. So, we now have to calculate the force that's required to move this object. So force is the same thing as mass times by acceleration. In this case, we are going to get force is equal to 200 kilograms times by an acceleration of 10 meters per second. So we get 2,000 newtons of force. Now we just have to use our work formula, and we get work is equal to 0.5 times by 2,000. So our work done is just 1,000 joules of force. Joules are, if you ever want to know what their actual units are, it's going to be meters squared divided by seconds squared. It's just it's because we're multiplying force times by a distance. So how much work is done whenever lifting a 11,000 pound object 35 feet off the ground? So the pound is really the English form of weight. So the English measure of force, really, or known as the empirical system, we use pounds. So this is really just the same thing as newtons, just in the American system. So we are going to call this 1100, and then we can now say, and because we're already given the force, we just have to multiply it by the change in x, or in this case, it's just 35 because it's going from 0 to 35 feet. And we would get an answer of 38,500. All right. And this would be in lb feet, I believe. I don't know if this has a way that you're specifically supposed to pronounce it. It's called a foot-pound, interestingly enough. So, anytime you see that it's called a foot-pound, I actually got the notation backwards here, but it's called a foot-pound. For whatever reason, very interesting, but you don't really need to know that for calculus. Alright. What about if we have a variable force? So our world is a very wonderful place. Forces are constantly changing, things are always in motion, things can be slowing down or speeding up, and all of this causes force to change. So, we have a new definition for work. Work is the same thing as the integral from a to b of f of x dx, where f of x is a function for force. So force, and this is just a random or like a good thing to know and something I'm going to be using several times in this video. So a force of a spring is equal to K, which is known as the spring constant. Spring constant. And then this X here is quite literally just distance from natural length. Natural length. Okay. Now that we have this, we can hopefully use these facts to solve some problems. So a force of 4 square roots of, or 4 square root of x newtons moves a box along a straight path. Calculate the work done. This is simple. We know work. And it doesn't look like we have a bound. Give me one moment to fix that. Oh yeah, it's supposed to be from 4 meters to 6 meters. 4 meters to 6 meters. Or sorry, 16 meters. So this is going to be the same thing as the integral from 4 to 16 of 4 square roots of x times by this little dx. Now this dx here is going to be the same way. We're really just multiplying it by the same change in x. It's the distance. We're just doing it at a much smaller scale, but we're adding up a bunch of tall intervals, or small integrals really. Intervals, not integrals, to evaluate the work. So what we're doing is we're evaluating a bunch of small intervals, which is really what the integral stands for, and then we're using that to evaluate the work and summing it up. So really what this integral here is going to evaluate to is, it's going to be relatively simple, but we are going to get x to the power of 3/2 divided by 2/3, I believe. Wait, nope. 8/3. And we're evaluating this from 16 to 4. Well, if we plug in 16, we are going to get 16 square rooted, which is 4, and then cubed, which is 64. So we're going to get 8 times by 64 divided by 3. Well, we're going to also be subtracting 8 times by, or divided by 3, times by 4 square rooted, which is 2, and cubed, which is 8. So what this is going to evaluate to is going to be, and I'm just going to say that this is going to be 64 thirds, so we can subtract this off and make this 7 times by 64 thirds, which evaluates to 149.33 joules. So now let's look at a spring. So springs exert forces on objects because they want to return to what's called their natural length. So I want you just to think for a moment. If you stretch a spring, it's going to feel, or it's going to take more and more force to stretch it out. All right. Well, in physics, what we do is the length of the spring that's like where we're not stretching it out at all, that's the natural length. And every spring has something known as the spring constant. or it might be another constant name. Give me one moment to search. It is called the spring constant, yeah. It's just been a while since I've done physics. So as we're stretching this, we're going to expect it to require more and more force. And because force is changing, work is going to be changing. You got that? So because force is changing, work is changing. So if we want to move an object from a certain point away from the natural length of the spring, the work required to do so is going to be variable as we're stretching the spring. So we're going to now have to use an integral to calculate the work. We can't really calculate the work without an integral. So a force of 10 newtons is required to stretch a 40 centimeter, or I suppose it's supposed to read a spring, not it. So a force of 10 newtons is required to stretch a spring 40 centimeters past its normal. I don't think that is supposed to be weight, but length. There we go. How much work is done by stretching it 40 centimeters? Okay, well, what we're going to do is first we need to solve this so we can get the spring constant, as we can't have two variables. In fact, this k is just a constant, but we want to solve for it so we can get that final amount of work needed. So we get 10 newtons is equal to k times by 0.40, I believe. Yeah. And you might be asking, why are we timesing it by 0.40? Well, newtons are in meters, however, centimeters are 1/100th of meters. So we want to get everything in terms of meters, or like length of meters. So what we're going to really find here is that k is going to be equal to 10 newtons divided by 0.4. So now that we have this value, which is really going to be the same thing as 25, we now just have to say, or we can now set up an equation for our force. So force of x is going to be equal to 25x. So work is going to be the integral, and we want to know what the work is at 60, from 0 to 60 centimeters, of 25x times by the distance dx. Well, whenever evaluating this, we are going to get work is going to be 25 times by 60 squared, or suppose I should show you the x's first. So x squared divided by 2, evaluated from 60 to 0. Well, this is going to be the same thing as 25 times by 60 squared divided by 0, or divided by 2, sorry, minus 0, which evaluates to 45,000 joules. Jeez, this is a lot of joules, isn't it? Very strong spring. You know what? We did do something wrong. I should not have evaluated this as centimeters. I should have evaluated this as meters. So this should all be 0.60 squared. And now we're going to get a much more reasonable answer of 4.5 joules. So long as I did everything else right. Alright, and then finally, the work required to stretch a spring 10 centimeters beyond its natural length is 12 joules. How much work is required to stretch it to 7.5 centimeters past its natural length, not weight. I don't know why I kept saying weight. Apparently I was tired when making this. Alright. So, we're going to say that work is equal to the integral, and this is a spring, so k times by x dx. And we're evaluating this integral from 0, it looks like, to 10. Or actually to 0.10. Because we're in centimeters here. And we know the net, or the amount of joules, is 12. So now what we have to do is evaluate this integral and then solve it for k. So what we're going to get here is 12 is equal to kx squared divided by 2 times by, or not really times by anything, evaluated from 0.10 to 0. Well, evaluating at 0 is not going to give us anything. So we're going to get 12 is equal to k times by 0.10 squared divided by 2. So 12 is equal to k times by 0.005. Now we just have to multiply this over. So we get, or divide over, so we get 12 divided by 0.005. Which gives us a spring constant of 2400. Now what we have to do is we need to find the work that's required to stretch at 7.5. So we're evaluating this from 0 to, really, not 7.5, but 0. Alright, so 0.75 times by 24. Alright. X dx. And this function here is going to give us the work required. So we get work is equal to 2400 times by x squared divided by 2, evaluated from 0.075 to 0. Evaluating this at 0 is just going to yield 0. So we just have to worry about the upper bound, which is 0.075 divided by 2. Alright, or squared. There we go. Now evaluating this, we get an answer of 6.75 joules. Which the interesting thing about this is, you can kind of see that this isn't exactly exactly, I forgot what I was going to say, but this is where I'm going to leave it off for today. I hope you all have found this video informative and interesting. And if you all need anything, or want to see any videos, I will love to take some recommendations for y'all. But I hope you all have a wonderful rest of your day and enjoyed this video. Have a great rest of your day. Bye-bye.